No.
It's going to be a little bit of a pickle. It's a challenge with just use of pointers. A pointer array of pointers.
Yeah, I know.
All right. What we discussed during the previous lecture was how if we guess how a particle moves, what is its position at an arbitrary instant, we could figure out what is its velocity and what is its acceleration. Well, we will see that if we the purpose of it is that if we want to design a particular trajectory for an object, we can figure out how it has to interact with the environment. So, for example, if we want to shoot a spacecraft to Mars, well, we know how Mars moves. We can figure out, therefore, how we want the spacecraft to travel. And from that, we can find out how fast it has to move and what accelerations it should have. And from that, we'll figure out how to fire the engines. Very often, we have a different situation. Well, we know that something will be passing through a space where it will experience a particular interaction. This particular interaction is going to affect the motion. However, the relationship between the interaction and motion, which we will use, says about acceleration, not about position. So it is that often we will face situations in which we know acceleration, and actually, because if you think about it, that equation which we use as an example, a quadratic equation for an object which I can throw over here. How did I know that? I guessed at this point, actually. I told you that this is I didn't really give a justification. We will have the justification for that motion is the other way around. First, I can figure out how an object interacts when it flies. From that, I can figure out acceleration, and now do a backward operation to find what is velocity of an object at an arbitrary instant, and then what is its position in an arbitrary instant. Do you understand me? Good. So today I would like to talk about how from acceleration figure out what is going to be velocity of an object or a particle, more precisely, at an arbitrary instant, and where it is going to be. Well, since not everybody is familiar with integration, I wanted first to start with a digression, because, well, integration is kind of operation reverse to differentiation. So if velocity is derivative of position, then position is an integral of velocity. Also, acceleration is derivative of velocity, therefore velocity is an integral of acceleration. And although actually in physics we use both definite and indefinite integral, most of the problems actually are based on definite integrals. So I want now to refresh or to introduce a concept of a integral of a function, and we will start with a numbered valued function. So let's say, for which we can make a plot. So let's say that we have a certain variable xi, and this is a plot of the function. So here we have f of xi. If I want to find an integral is a definite integral for a number valued function, depends on the function and the choice of the interval in which we integrate. So these are two arguments. You have to know what function you integrate and over which interval. Now let's say that I'm going to integrate a function along this part of the domain. What we have to do when we calculate, here is formally how we write it. Now I want you to comprehend what's written over here. Let's start with this expression, just this product, f of psi I tilde times delta psi I. What does it mean? We have to divide the interval over which we integrate into smaller pieces. Now, for each, and I will use symbol I to identify the pieces. So it says 1, 2, 3, 4, 5, 6, 7 over here. So really, I have 7 different pieces here. Now, for each piece, I multiply the size of the piece, which actually means the difference between these two arguments, by the value of a function at a point from that tiny interval. So I take some point psi I tilde must belong to this particular interval. Well, now I multiply those two. So I take the value of the function and multiply size of the interval by the value of the function. So if you think what geometrically I'm going to get the area of such a rectangle. Can you see that? Now I have to do it for every piece. For every piece I have to calculate such a product and then add all of those products, which means that I will geometrical interpretation will be that it is going to be the area of all those 7 rectangles. So I took care of this sum. This sum, by the way, is referred to as, those of you who had calculus, can you shout? Riemann sum, correct. So this is a Riemann sum. We call it a Riemann sum. And let me remind you that when we construct Riemann sum, we have to divide the considered interval into small pieces. For each of those pieces, we have to multiply the size of the piece by the value of the function at a point which belongs to that piece. Well, that way we will get some number. After we have this number, we have to make another division. We have now to divide it, let's say, into 20 pieces and repeat the procedure. We will get another number. We have to divide it into 50 pieces. Repeat the procedure. We will get another number. And if we have to continue dividing that interval AB into smaller and smaller pieces. All of those pieces, the size of all those pieces has to converge to 0. And every time we will get a certain number, so we will get a sequence of numbers with narrower and narrower dimensions of those rectangles, I mean the widths of those rectangles, and eventually we will have to add them. Well, so if we add them at the limit, the rectangles are going to be so narrow that actually you won't even see that horizontal side of the rectangle, and that way we will get really area of that figure marked by 2 vertical lines, horizontal axis, and the plot of the function. That limit is referred to as the definite integral of function f over interval AB. Say it to your neighbor. What is it? I buy that you can say it also. It's a definite integral of the function from A to B. You don't have to say over AB, from A to B. All right. You can also think about, so geometrical interpretation is that it's the area of that figure over here. I also look at that it's the sum of all values of the function, because I mean this when these value, it's weighted really, it's weighted average of the function. But if you think that in the limit the horizontal dimension of the rectangle approaches to 0, it's like measuring the width of a point. So it's for each of those terms in the Riemann sum, you multiply the size of the point by the value of the function. So practically we are adding the values of the function. So you can also think that it's the sum of all values from A to B. You cannot add those numbers any other way. Why? Because too many of them. There are more numbers between number A and B than natural numbers. I mean, if you get into theory of numbers, as humanity, we can already distinguish between infinities. There are larger infinities and smaller infinities. And this is the second, the number of points which we have over here is not the smallest infinity, it's that larger infinity. Because for the smaller infinity we can calculate, we can calculate infinite series. But here we cannot even make an infinite series because the number of terms cannot be numbered with integer numbers. All right. So this is how we calculate integral, definite integral of a numbered valued function. Well, acceleration and velocity are not numbered valued functions. They are what? Functions. A what? Vector valued functions, right. And we will have to learn how to integrate vector valued functions as well. So, in the way we write it, it's identical. Obviously, this plot does not make sense anymore because we cannot plot a vector valued function. If we want to plot a vector valued function, let's say that we are talking about three-dimensional vectors because this is what concerns us most. We would have to make three separate plots. Three separate plots for what? For the components of the vector. So we could make a plot for x component of the vector, y component of the vector, and z component of the vector on three separate plots, provided that the argument is number, like time, for example, which will be fine. Because if it happens that argument is a vector as well, then we have to have how many plots? No. 9. For each argument we will have 3, right? And we will have 3 arguments now, three number valued arguments. Therefore we will have to have 9 plots. All right. So don't think now the definite integral of a vector valued function is that its geometrical interpretation is somehow related to the area on that graph. Don't think about any geometrical interpretation for this integral. Well, we also have to make Riemann sums. So we take an interval of the variable and multiply by the value of the function. However, this time it's a vector. Now, can we multiply it? Say yes or no. Yes, we can multiply. The result is going to be what? A vector, correct. What symbol did we, if we wanted to use unambiguous notation, if we use the symbols which I introduced here for unambiguous notation, which symbol would I have to have here? The bullet, correct. So here will be the bullet. All right, so the result is going to be a vector, and the Riemann sum is going to be a number or a vector? A vector as well, correct. What addition would we have to use? Let's say that if we use the unambiguous notation, how that plus should look like. Plus in the circle, it's addition of vectors. And the result is going to be a vector. If we add all those vectors, we will get a vector. The Riemann sum in for a vector valued function is going to be a vector. Well, for a particular division, we will have a certain value for that vector. We have to make a smaller division. We'll get another vector, and we will continue doing it. We will get a sequence of vectors which will converge to a particular value. That, whatever that value is going to be, will be the definite integral of that value, vector valued function. All right, so this expression over here is a vector or a number. Who votes that it's a vector? Who thinks that it's a number? Those of you who thought that it's a vector, you are right. Correct. Definite integral of a vector valued function of is going to be a vector. All right. Now, we very rarely, and particularly here in physics, we will not use the definition of, we have to know what a definite integral is, but we will never use the definition to calculate those integrals. So we will not construct Riemann sums and calculate limits of those Riemann sums to find the definite integrals. And it is because of a very important theorem in calculus, which is called the first fundamental theorem of calculus, and it allows us to find values of definite integrals for a large class of functions. And in physics, fortunately, we have mainly these functions. In mathematics, you can find the functions for which you cannot use this theorem. But for our purposes, in most cases, we can use the first fundamental theorem of calculus to find definite integrals. And in order to find definite integrals, we have to know the value of indefinite integral. And indefinite integral of a function is such a function that if I integrate it, I will get the original function. Probably it isn't clear. So how about if I write an example? Integral, indefinite integral, and for indefinite integral, the major difference between definite integral and indefinite integral is that indefinite integral is a function. It has still a variable. So for example, let's say that indefinite integral of function x is going to be 1/2 x squared. Let's say, yeah, so here we have function f of x equals x, and then indefinite integral is half of x squared. Note that on this side we got a function. We still have a variable in it. If I put a limit over here, let's say from 1 to 2, I will get definite integral, but result is not going to be a function. It will be a number. So I shouldn't put these limits over here. All right? If we think about number valued function, if we calculate the definite integral, the result is going to be a number. If we calculate indefinite integral, we will get a function. Make sure that your neighbor comprehended it. What did you say?
Do you have to take account plus the constant if we're doing indefinite?
For definite integrals, we don't care. Yeah, you are right. Yes. For indefinite, yeah, okay. Somebody brought up actually, and this is a true statement, that if a certain function is an indefinite integral of another function, then if we add a constant to that indefinite integral, it is also going to be an indefinite integral of a function. So for example, like indefinite integral of x could be 1/2 x squared, but if I add 5, it's going to be, it's true as well. I can put 10 or whatever. So in many books or tables, actually you can it can be written that indefinite integral of a function is another function plus a constant. For calculating because for our purpose, I mean, the purpose of having indefinite integrals is that we do not have to calculate limit of the Riemann sum when we are looking for the definite integral. Consult with your neighbor that he or she comprehended what I just said. All right. So the purpose of the first fundamental theorem of calculus is to find definite integral if we know indefinite integral. Now, I know that you don't know those integrals, those indefinite integrals, so you probably think that the task is as difficult as calculating definite integral directly from the definition. Well, at the back of the book, you have a table of indefinite integrals. So we will use that table without deriving indefinite integrals. You will do it sometimes in calculus. So we will just use the fundamental theorem of calculus. If I have a certain function, let's say f of t, and I want to find definite integral in interval from a to b, I have to take indefinite integral. I wrote here f of b. F is indefinite integral. As I could actually over here write, and so f of x is equal integral of f of x dx. So I have to take indefinite integral and just know the value of that indefinite integral at two arguments. The two arguments which correspond to the ends of that interval over which we integrate. We call them limits. So we have to find out the value of indefinite integral at the limits of definite integral. Let's take a look at an example. How about if we take a simple function? What did I take over here? Oh, okay. Let's say that it's a linear function. And this function, if I take argument c, the value of the function is going to be h. And at argument 0, the value of the function is going to be 0. And so the function at any point between 0 and c value of that function can be calculated from this formula. You see that it works. If I plug in 0 for x, I will get 0. If I plug in c for x, I will get h. Do you see that? And it's a linear function. This is a linear function. So value of the function increases proportionally to the argument. And now I will calculate integral of this function from I mean, there's too many of those. I forgot to erase that. So erase this part. Cross one of those. Yeah. Here I have the function. I integrate from 0 to c. I say that I integrate with respect to variable x. Indefinite integral of this function is going to be 1/2 that quotient multiplied by x squared. Well, so if I plug in now the limits 0 and c, if I plug in c, I will have h c squared over c, so c and c cancels. 1c cancels, so I'm left with 1c. And if I plug in 0, the value of this value is going to be 0. So result is going to be 1/2 times c times h. So it is 1/2 times the length of the base of this triangle times height of this triangle, which actually should make us happy. Why? Because it's the area for the of a triangle, right? So really we calculated the area underneath the triangle formed by that plot. All right, now I want to use the fundamental theorem of calculus to physics finally. So I finished the digression. Now we're back to physics. Well, since velocity happens to be well, if we differentiate velocity, we get acceleration, which means that velocity function is an indefinite integral for of acceleration. So if I want to find integral of acceleration, so let's think kind of backwards. If I want to, I mean, maybe I didn't do the derivation over there. So if I think about trying to find out definite integral of acceleration, according to the fundamental theorem of calculus, I should take indefinite integral and calculate it at the two instances, t1 and t, right? And subtract those two. So integral of acceleration will be velocity at instant t minus velocity at instant t1, right? So on the other side of the integral, I should have a difference of velocities at the two limits. Well, I will move one of those velocity to the right. So now I can write that velocity at instant t is equal to velocity at instant t1 plus integral of acceleration from t1 to t. Right. Now let's think what is what of what over here. So by t, I understand an arbitrary instant. I can vary it, which means that v of t represents velocity of a particle at an arbitrary instant t. Well, in order to get that, I need to know velocity at a particular instant. So it will be velocity at this particular instant plus integral of acceleration from that particular instant to the instant at which I'm interested in velocity, which I'm trying to determine, of acceleration. So how many values of acceleration do I have to know, by the way? No? Not two? More than one? More than two? More than three? All of them between t1 and t. Correct. I have to know all the accelerations It's not sufficient to know just one. So, for example, if I want now to figure out velocity of this pen after I release it, and so I release it with a certain velocity, and it is flying over there, right? I know what was its I can determine how fast I tossed it. So I will know velocity at the instant at which I released it. Now I could predict what is its velocity at an arbitrary instant, provided that I knew its acceleration over entire trajectory. It is insufficient that I knew acceleration just after it left my hand. I have to know all of those values. Well, fortunately, we can figure it out. Because like with this pen, you still don't have a firm physical justification, but just from the fact that what I told you last time, that it is moving according to a quadratic function. So what was the acceleration of that object? Let's say at the highest point. Was it up, down, or 0 at the highest point? Who thinks that it was down? Who thinks that it was up? Who thinks that it was 0? Those of you who think that it's 0, you are wrong. It's down all the time. And actually, I know that it is, that because right now you know it just as a piece of trivia. I told you this last time. So we had this discussion, and I was trying kind of convince you, although really the firm justification, which will clarify the acceleration at the highest point in your head, will occur when I will really start to talk about interactions. So you will recognize that actually it's obvious that at any point where as long as it is flying, acceleration is down and has the same value. All right, so I could figure it out because I knew what is velocity of that particle, because I knew all accelerations. Now, very often actually for this T1, we will select a convenient reference of time. What will be convenient reference for time? I mean, 0, to assign value 0. So for example, like in the motion of this flying marker, I would say that at the instant of release, we turn on the stopwatch. So at that instant, time was 0. All right. Because velocity is equal to the derivative of position, so if I use fundamental theorem of calculus for the relationship between velocity and position, again, let's start with the right-hand side just of that integral. Integral from t1 to t, and actually this t1 doesn't even have to be the same as the other one, so you can put t2. Actually, it would be better even. I'm going to change it. So integral from t2 to t of velocity would be equal to the value of indefinite integral of velocity, which position happens to be the indefinite integral of velocity at instant t, minus the value of indefinite integral at instant t2. So now I can move this t2 to the right hand side and again have an inverse relationship between velocity and position. So in order now to find position at an arbitrary instant, I have to know where the particle was at a particular instant, and I have to know velocity at which instant. All of them between that instant when I knew the position and the considered instant. Well, we are going to calculate, when we calculate position and velocity, going back from acceleration. Yes, so from acceleration we can find out velocity. From velocity we can find out position. Well, we will have to integrate vector-valued function. The simplest way to perform this operation will be to use arrays, triads of their scalar components. So I want to make a digression now how to calculate integral, definite integral of an array. And each argument, each number in the array is a function of time or of certain variable. All right. So directly from the definition of definite integral, I wrote that integral of this array is limit of the Riemann sum. Now for that Riemann sum over here, the value, it means that I have to select all scalar components of this vector at this particular interval. Now I can recognize that I'm multiplying this array by number delta ti. I'm not going to use, by the way, distributive law, because some of you thought that this would recognize that multiplying this delta t by each of the scalar components is distributive law. This is not distributive law. Distributive law always refers to one operation over another operation. Here we have only one operation. Okay, so I can multiply each of the scalar components by this number and combine it into the Riemann sum. And when I calculate limit of sequence of vectors, it means that each of the component is going to converge to something. It means that I will have that each component is going to be limit of a certain Riemann sum. For the first component, it will be Riemann sum constructed from first component of the integrated vector. Second component is going to be limit of the Riemann sum, where we use where the function is the second component, and so on. Well, I can recognize now what is that. What's that? Limit of the Riemann sum of a function representing first component of the vector. So what's that? It's the integral of the first component of the vector. Now, this, so I can write it down that way. So look, then when we calculate integral of a function, a vector-valued function, we get a vector whose scalar components are equal to the integrals of those components. So each component of a vector is integrated separately. Look that it is very similar to what we did last time, except that last time we were calculating derivative. Derivative of a vector function requires that we calculate derivative of each component. When we integrate a vector-valued function, we have to integrate each component separately. How about if I now go to an example and thank you. Can I erase it now? All right. So why don't we start now? Let's consider tossing this, tossing the pen, which I just did a moment ago. Well, so acceleration, and we will find a good argument when we start to talk about interaction. Acceleration of an object flying in this classroom is constant. And if we introduce a smart coordinate system, I mean, it's not smart. If we are smart to use a convenient coordinate system, I will choose, let's say, x component in this direction, y component in this direction, and z component in this direction. So acceleration, we will see that acceleration, the reason why it is, but I think that most of you believe now that acceleration is down. Precisely, it has value, with the accuracy of 2 significant digits, it's 9.8. Why don't we go just for 1 significant digit? So instead of 9.8, I will say that it's 10. So acceleration will have components 0. Now, since I picked y to be up and acceleration is down, so the vertical component of acceleration is minus 10, and z component is 0 meters per second square. All right, let's now find out what is velocity as it travels throughout the space. Well, first of all, I would have to determine what is its initial velocity. So when I released it, right? Let's say, and when I released it, let's say I released it in the xy plane. So z component is going to be 0 meters per second. And let's say that I tossed it at an angle 45 degrees, so then both components are equal. And how about, although we can put any 2 numbers over here, it doesn't matter. So let's say that I toss it with 2 and 2 meters per second. So vertical component and this horizontal component, where let's make one 3. So it was not at 35 degrees, but at an angle like that. All right, let's find out now what was velocity at an arbitrary instant. Well, so in order to do this, what do I need to know? I need to know velocity at a particular instant. Do I know it? Yes, I know the velocity at the instant when I release it. And I need to know acceleration at all instances. Do I know it? Yes, because it's constant. All right, so velocity at an arbitrary instant is equal to velocity at an instant t1. Oh, why not? Plus integral from t1 to t of acceleration. Now that in order, you don't have to do it, and actually in a calculus book you won't do it, but just to make sure that you do not confuse the upper limit with the argument over here, I put even prime here. Do you understand why I put prime? Because what is this t in English? It is the instant in which I'm interested in velocity. Now what is this t? With this t, I have to all instances from instant when I know velocity to the instant where I'm trying to determine velocity. All right. Now, so it's going to be, I will just copy this one, and I recognize now that acceleration, this is really acceleration at instant t. So it's constant. So I can write down that I have to now integrate a constant over here. Well, if I integrate a constant, I can take out that constant in front. Have integral from t1 to t of dt. Now, what is indefinite integral of dt? We will have to take a look at the tables, and you will find out that it's t. So it's t, and then I have to calculate difference. T prime specifically. Integral would be t prime. Now I have to plug in values for t prime corresponding to the limits. which means that over here I will get t minus t1. Well, if I'm smart, I will turn on my clock at the instant when I release it, so t1 would be 0. I can say that t1 is 0. So this one over here is 0, and after simplification I get that it's v plus at. And now I can write down explicitly this is 230 meters plus 0 minus 10 0 meters per second squared times t. We got a linear function, which should make us actually pretty happy. Why? Because this is what we saw last time. Yeah, what operation did we do last time between velocity and acceleration? The other way, correct. Yeah, so we took such a form of velocity, we calculated derivative, we derive acceleration. So obviously now when we do it in a reverse order, it has to agree. If it didn't agree, we should be unhappy. And actually, if it didn't agree, it would mean that we did something wrong. All right, so this will be all for today. Thank you very much, and see you tomorrow.